of people in a big city, then where you can see that the human has to avoid other, has to change the trajectory, has to sometimes people stop and start talking with other people. That is a typical situation that it is seen in a city, in a crowded city. In this case, it's Japan, but can be in any of our cities. And then we can handle this situation in robotics. Not simple situation, but also this kind of complex situation. How we do that? Or, for example, what we can do, it is our robots has to help elderly people, as you see here in the left, or have to carry baggage of, in this case, the children's, or go shopping, or do this helping, in this case, also elderly people, or other kind of things like these ones, where robots and humans interact. And that is something that now looks like a science fiction movie, but in the near future, we're gonna see many of these robots in our daily task, in daily life task. And what is gonna be that? That is what we are doing research and trying to understand what means this kind of interaction, what means what the robots has to do, what the humans has to do, how it both has to behave in order that this can be really the tool of the future. You have to think that mobile phones has appeared not many years ago. And before the mobile phone, many people it was interacting directly physically. But now through the mobile phone, people is doing many of the things through this interface, this mobile. And now people has adapted to that and looks that is very normal. In the future, our robots will be something similar. You will see that the robots will be in our house, it will be in the buildings, it will be in the streets, and that will be not a science fiction like science fiction film. That will be a real life thing. How long is going to be that? That is going to take time. That's clear. That is not going to be tomorrow. But you can see now the Roomba. This is cleaner robot. Yeah, you can see in many houses. In the future, this will be something like in many applications. You will see this kind of robots in the restaurants, in the factories, in the streets. For example, last mile delivery will be robots that will deliver the goods that are bought through internet. Then you will see that this kind of delivery will be done by robots. Now we have, for example, one of these projects doing this kind of things. Okay, now you can see here. First is a robot that has nearby humans, and that is called coexistence or cooperation between humans and robots. But you can do something else. You can interact between the robot and the human can interact doing so. So for example, here, a handover operation, the robot gives something and the person pick up, or vice versa. Person gives something to the robot, and the typically kind of human-robot interaction and collaboration. And in this case, the human and the robot has to share the goal. The goal is, for example, in the handover is give the object, and the role has to share that. They have to combine who is gonna give, who give, for example, the object, what we call is the master, and the person that receives is the slave in some way, or could be completely cooperative. Then both cooperate, giving and receiving some in this case some object. No? Okay, now let's going to explain in more or less detail, not too much detail, different human-robot interaction and collaboration topics. One is a company, how a robot and a person do this accompany. This accompaniment is, in this case, the robot controls, and the human itself also controls how it has to be doing this accompaniment. And I will explain how we do that, or how we do the approaching, or how we do the searching. We look, for example, we try to search something, an object that is in a large area, and how we can do the search between a human and a robot, or the handover. how we do the handover operation. Also, we will explain this kind of human robot then transport an object. In this case, it's a light bar, then it's transported by both. How they do this task. And also, we will present the preliminary works that we are doing in harvesting between robots and humans together, how we do this operation of harvesting. Okay, now let's start, but a new focus of how this kind of human-robot interaction has to be done. And we see in the first, in this case, a case of two agents. One agent could be the robot, and another agent could be a human. And they want to do one specific task. For example, let's going to think about the handover. There is a person is going to give an object to the robot, and this robot has to. The goal is that to give this object, and the robot will finally pick up the object, and the person will release the object in order that the person can have this object. This is a collaborative task where both has to, in some way, has to show how they can help each other in order to arrive to this goal that is giving the object. In this task, there are different functions. The first one is the perception. The agent, for example, the robot, has to perceive what is in the surroundings. What is the person? Where is located the person that has to give this object? What are the obstacles that are in the room in order that when it moves, it avoid these obstacles? And what is the object that has to be picked up? That is what is perceived about the sensors of the robot. In the other, there is the intention. Intention is because the person has intent to give the object to the robot. That is the typical action that the robot is expecting, but could be that the person is not, the intention of the person is not that. Could be that the person don't want to give the object. Why? One of the issues is because when he's trying to give the object, it falls down. And then the object, instead of following the trajectory that is expected, is doing another trajectory. That could be one. Another is because the person decides not to give the object. And then in this case, there is no collaboration. But the robot, what is going to do? It's going to stop. It's going to try to pick up the object. What is going to do? And then in some way, the robot has to perceive the intention of the person, or it has to, or the person can tell that I don't gonna follow that, and I don't give you the object. Okay, and then the robot is gonna do another thing. Okay, sorry, I didn't show this. Okay, the point. Now, this is the first part, perception. The second part is situational awareness. The situational awareness is the robot has to understand which is the current situation. The current situation means that the person is following a trajectory where the robot is going to be able to pick up the object. And then that is what it has to be perceived by the robot. This situation that the trajectory of this object is moving in the right, what is expected by the robot, and then the robot will move the arm, will move itself, and also will move the arm in order to pick up the object. That is what is expected. But could be that something else is happening. For example, another person is moving around, and then this also has to be perceived by the robot. Because if that is, this person can collide with the other person and is giving the object, the robot has to realize that is something is happening, and then has to change the motion. Could be that it stops, or could be that it's gonna avoid that, and that has to be perceived here. But also, the robot has to perceive what is gonna be the future situation. I said the future situation is when the robot is perceiving that the object to be received is moving in the right trajectory, it will predict what is the next position of this object in the future, in order that the robot, can know what is going to be the object in the future. That is something that is here in the future situation, and that is what is called situational awareness. The concept of situational awareness is a concept that was developed for flying, for the pilots in the war, for the pilots, in order to decide what is going to be the other airplanes, and what has to be taken in account and what has not to be taken in account. And this concept has been spread and now is used in robotics and many other areas as one of the issues to understand what is the current situation and what is the future situation of what is going to happen. And then the next is decision making. Decision making means what the robot has to do, because the robot knows what is the task to be done, what is the objective, what is the development, what are the constraints, and what are the skills of the robot, and what are the skills of the human. And then he can make the decision what to do. In this case, in the case of giving an object, that is when the robot will predict what is the future of the position of the object, and it will plan. Plan means do the action, the motion of moving the robot arm to the position in order to pick up the object at the right time. Okay, but this task is not done only by the robot itself, but is done also by the human. And then in some way, the robot has to understand what the human is doing. And this is done here in the situational awareness. It understands here what the human is doing, and then it takes a role. And this role could be master slave. Master means that the robot, for example, the person is giving the object, then in this case the person is the master, and the robot is the slave in a way that the robot is trying to follow the prediction of the trajectory of this object and then try to pick up. No? But could be collaborative. Collaborative means that both collaborate to do the task, and both has some skills that the other do not have, and then they can share the skills in order to do the task. Or could be adversary. That is what I say, the person decides not to do that, or the robot decides not to do the goal, okay? And then with that, you can both elaborate what is going to be the plan. And the plan could be a plan that has been already learned, that established plan, or could be that the robot adapt to the situation, or could be that the robot anticipates what is going to happen and then change its plan. And that is typically, for example, if you know in tennis, in a tennis tournament, then there are two players, okay? And then if you're one of the players and you try to you have to take a look of your adversary, that is the other player, what is gonna send the ball, and then you have to anticipate to start running before the ball start to go out. Why? Because it's the way that you will arrive on time to pick up the ball. And that is one example of anticipation. In humans, or do many times this anticipation. That has to be done here. And then be proactive. That is another typically way to do to proactive actuate with respect. And then from that, there is the collaborative actions, and that follows. And that is the cycle that is repeated many times in the human-robot interaction. Okay, we will see that in the next slides in different examples, and you will see what means that. Okay, well, first, in order to understand what happens in collaborative AI, and where humans collaborate with other humans, or humans collaborate with robots, or robots collaborate with robots, okay? There is also a decision making that is the center of everything. Then you do the action, and you do the perception, and there is interaction, and there is communication, and also there are learning and adaptation. And for example, in perception, the main tasks usually are recognize the environment, identify and track people, and interpret the situation. And there is also cooperative perception, where there is not only the robots take a look at something, but also could be there are sensors, for example, a camera in a building that also detects something, and then this all information, finally you create a cooperative environment perception where the information from different agents, in this case two robots, and also from the floor, this camera, give the information about to track, in this case, for example, to track this person here, okay? And another issue of that is communication, and communication is through a dialogue that could be a speech, text, or visual, could be non-verbal dialogue. For example, non-verbal dialogue, it is, in this case, for example, this robot is detecting the position of this person using a LiDAR. LiDAR is a laser beam that can detect the distance between the sensor and everything that is outside the sensor. In this case, the legs of the person, and this can realize what is. Or could be that is a direct contact, physical contact, like these two robots that has contact through a sensor, and then in this case, it can detect what is the force that is exerted by the other sensor. And there is a typically non-verbal dialogue. And also there could be implicit communication. And in decision-making, there is reasoning and planning. Reasoning is to reason about the information that you have, could be reasoning about geometric information or physical information, or could be reasoning about other issues of the task. And planning means to do a plan of the different actions. For example, when you do a trajectory planning, you do make a sequence of actions in order to go from one place to another. Okay, a robot could be in a room and it has to go to the lift, and then it has to plan what is the trajectory that has to follow to reach the lift, because it knows the map of the building. Okay, that could be a typically. Also, in decision making, you have to know the intentionality of the person. If the person really wants to follow the plan, then typically it has to be done. For example, the handover is going to give the object or not. It's going to do the reverse. It's not going to be the object. Okay, and also there has to be an agreement. Usually, when there is a robot and human collaboration, it has to be an agreement, implicit agreement or explicit agreement of the task to be done. In the case of the handover, there is an agreement that I'm going to give the object and you're going to pick up the object. But in another cases, could be another kind of agreement. If you carry out one table between a robot and a human, the agreement is to follow always the plan to move the table in order to avoid the obstacles and to go both together with the table. Okay. Now, what else? And there is also interaction. Could be social interaction. That means follow the social rules. That are, for example, if you walk outside, you know that in Europe usually the person goes to the right and the other who is coming is going to the left. That's typically, but in Japan is the reverse, and that has to be known. And these many other social interaction. Physical interaction means physically there is contact between the both agents. This contact because there is an object in between. They are carrying out an object between both, or both, or taking together the hands and doing something else, or could be also human-robot interaction. Okay, now let's going to see some experimental settings where we do these experiments. There is two robots, TV and Davo, the two robots that we use, but also we use Evo, that is the other robot with two arms with 6 degrees of freedom. And there are some places that are located in the North Campus and the South Campus. This is North Campus site, and you can see the human and robot what we do. And also we have the soft campus that is besides our labs. Then we do also experiments, and that is okay. Now let's go into see robot sensors, what kind of robots we use. And I explained that with this TV and double robots that has GPS. It has a stereo camera. A stereo camera means something similar to what we do. We do with our eyes. We have two eyes, and that allow us not only to identify the object, but also to compute the distance between our hand and everything that is surrounding using the stereo vision functionality. And we have in this case a tactile screen where we give information to person, or can be also a person give us information. We have these leaders of the sensor, these sensors or the sensor that give information about the surroundings. And it's, as I say, this leader give us depth information, okay? And with that, we can navigate, localize ourselves, and also detect obstacles or detect moving objects. Not only with this leader, but also with the stereo camera, also we can do that. And also we have encoders that give also the position, that is encoders or a sensor that detects how many, how the rotation of the wheels. And with that, we can know how many meters we have moved around in front, or how many meters we have rotate, or what is the curvature of our turn. Okay, that is, and also evidently we have computers that do this computation in real time. Real time, when we talk about real time, is around 30 milliseconds up to 150 milliseconds. That is typically real time. But if something is moving very fast, real time could be 1 microsecond. Okay, that depends on what we want to detect. Okay, and then here in the EVO, we have also the sensor of the arms, and also we have force and torque sensors, in this case only here in the wrist. There are some sensors, some robot that has also force and torque sensors in the joints of the arm. But in our case, in this, we have only these force and torque sensors in the wrist. I showed that because we will use this sensor for doing some of the tasks. Okay, let's go to one example of intention prediction anticipation in human robot accompaniment and approaching. Okay, in this case, the goal is to accompany a person. Okay, we want to accompany a person when we move around. That is a typical thing that we see every day. Every day we are moving, we are walking, and it could be that we have with a friend that we are moving together, and we are doing this kind of accompaniment. Okay, in this case, we have a robot. In this case, I show here with 2 persons, but it doesn't matter. It could be 1 or 2 persons or several persons. And then all together, this group of the robot and 1 or several persons wants to go to a goal that is this goal. And then they want to move. The plan is, for example, to follow this track straight forward. Then this is the line to go. However, in this case, there's a person that is moving around. And if we try to follow this motion, that could be that we collide with it. Then what we can do? Then what we have to do, well, first, we have to know what is the intention of motion of this person. What is because we know the velocity through our sensors, we can compute where this person it is, where is located, and also what is the velocity of this person, and what is the trajectory that we can predict that it's going to do. And also, at the same time that it's doing that, because we are doing a company, we have to know what is the intention and the motion prediction of this person, the person to be a company. Because the person to be a company could be then follow us, or could be that it's not, then it stops, or could be that it moves back. And what is going to do this person, the robot has to take in account, because the next motion will depend on the person to be a company, and also depend on the rest of the people that is here. People, bicycles, cars, or whatever is moving around. Okay, now once has this information, that is what is called situational awareness, then it has to do the plan. And the plan is, what is the next motion? There is different plans. You see different trajectories. One is going straight forward. Another is to take this path. Another is to take this. Another is this, and this. And the robot, every time, has to compute all this path and take a look of this and decide which is going to be the path that has to be followed. Because when this person is moving, this other person also is moving. And then when this robot, the person with a company person will be here, probably this person will be here. And then it can take, for example, this could be the right path, okay, to follow. In approaching, it's something similar. In this case, if the person stay in the same place, then the robot has to look what is the best position to be in front of this person. Could be this, or could be this, or could be this. And there are different trajectories. This trajectory, this one, and this one. It has to decide which is going to be the trajectory to move in order to locate it in a place that can approach and finally stop to talk with these persons. Okay. Okay. Now, what do we have here?
Alberto, perdona, you have a question here about from Carla and Angel in the chat. Can the stereo camera replace an ultrasonic sensor to detect objects?
Excuse me.
You have the chat and you have a question here.
Okay. Okay. Just a moment.
You have two questions at the moment.
Okay. Can the stereo camera replace the ultrasonic sensor to detect objects? Yes, actually, the stereo camera is a typically sensor that we use. We use LiDAR and we use stereo cameras. Ultrasonic sensor only used for very short distances, and it only detects if you have an object very close to you. But usually it's not used for long-term distance. You can use that, but it's very noisy sensor. Okay. And Angel say that use about something. Okay. So okay. Ikeshi say in poor lighting condition, an ultrasound sensor might be better choice for object detection. So instead of replacing any sensor, could be advantage when you do it. No, as I say, usually we don't use ultrasonic. Is very poor sensor. We use LiDAR. LiDAR is very good because LiDAR, you send a laser beam and you receive the information from it. And that is very, very robust. And and that is what we use. Or we use LiDAR or we use stereo cameras. And the stereo cameras, there are stereo cameras with what is that? With the light waveforms, or you can use infrared cameras. Infrared cameras can detect at night a very poor condition, illumination condition, where it's a human or where it's something that is heating. Okay, and that is what we use. I repeat, ultrasonic sensor we use very, very, very seldom, only for very close objects. And a laser beam sensor usually is in rotation. Yes, a laser, the typically LiDAR use a rotation mirror, but the last ones are state LiDAR that has solid state technology, then don't use any rotation device. Okay. Okay, if you have any other questions, please let me know and we will follow. Okay, let's going to see this case of the human robot company approaching, and you can hear the robot and the robot agent and the human agent. Okay, and here you have the situation awareness. Here is the collaborative roles and cooperative plans, and finally the collaborative action. And here you have the human has an implicit intention, for example, the motion of the arm. And also the pedestrians that you saw before, also you can, they are giving some implicit intention by moving, by how they move. And the robot sensors detects these persons and also detects the human motion, and also detects the obstacles. All this is detected through the robot sensors. Okay, this is going to situation awareness. And this, with this information, the robot understand what is the current situation of the pedestrians and the human, and also the human arm. Okay, and then it can predict what is going to be the future situation of what, of the pedestrians, what is going to be the next in the few seconds, what are going to be this person, and also what is going to be the motion of the arm, for example, or the motion of the human agent. This is done here. And then, for example, we use, and I will explain a little more later on, it use something what we call social forces. Then what is the goal? Then is the something that is called the attractive goal, and also the adaptive force that given by the person in order to attract, and also what are the repulsive forces by the obstacles on other people. And then this is what you compute these forces here. These forces here, and you can see here, it is computed through these formulas, okay? And then with that, you know what is gonna, with this, that's the consequence of the current situation understanding. And then from that, you can do your collaborative roles and collaborative plans in order that the robot can accompany, in this case, the human, avoiding persons and avoiding obstacles, okay? And this is what we call human intention and situation prediction. And it is here you can create the plan, what is the next trajectory that has to be done. And I'm sorry. And then what is the next trajectory? And then you can do the collaborative action. And the collaborative action in this case is moving together with the person. That is the final goal. Okay, you can see here an example, and it's a video. This is a robot moving around. And then this robot has to detect the person that are around here. And it has, in this case, it's only navigation. And you can see this is like a vortex. And that is the future prediction, what is going to be the people. And the robot can change this motion, taking into account where the obstacles that are around, what is you see that the robot is slowing down, although it's going very slowly because safety issues. The robot is detecting always where is the person, the people around, and can predict what is going to happen. And you can see here that if people is crossing around and the robot is changing its motion because it's anticipating what is going to happen, and then it can change its trajectory in order to find the best trajectory to arrive. And then it's changing every time and adapting every time because it anticipates what is going to happen in the future, okay? And that is, that is one example of these kind of features. Okay, now you can see here the accompanying of more than one person, okay? There is two persons. I will give, here is approaching to these persons, and this is done always in real time. Everything is computed in real time, although the robot motion looks like that is a little strange sometimes, but it is something that is what is happening. Okay, you say, Carla, yes, okay, what is that? Janet says the leader is similar to sonar using the chips. No, sonar is the wave is going to the speed of the sound. Okay, LiDAR is going to the speed of the light, and LiDAR is a beam that is direct. It's only one beam, and the sonar is a wave that is propagated quite high, and you receive from different points. And all the summers showing using ROS. Yes, we use ROS everywhere. Okay. We are using ROS 1. ROS 2, still we have not used, okay? Now, you can see here, this is the example of robot accompanying approach. Now, here I will show a little more in detail, but because we have not too much time, I will show you this human prediction, how it's doing this. The robot is moving, Okay, the robot is moving, has to arrive to, and is detecting the motion of the humans, and is using what we call the social force model. Social force model, or virtual forces, it says to be in real forces or virtual forces, that we use in order to move our robot. In this case, the robot is this, what you see here. It has to arrive to this goal, and then it has an attractive force from destination that attracts this person, or the robot here, this person, to go to this position. But at the same time, this object, this robot, this other person give repulsive forces, and then the summation, the resultant force, has to be a force that brings this person or the robot or whatever to the destination that is this. Okay, and this is computed. That is the final, that what we want to get, and that is the final that you have here, and that is composed by the steering force, that is the force to go, attractive force to go to the destination, and is computed using this formula, that is the speed, expected speed of the robot and the real speed of the robot, and that is this difference is what makes that to go to attractive force to go. And there is the interaction forces, that the forces then usually are repulsive forces, then try to push out the robot from the object and from the other moving, that could be a robot, it could be a bicycle, or could be another person, and then that is try to avoid it. Okay, and then finally that is computed by it's an exponential decay function with the direction of the trajectory. Okay, in this case is this one. Okay, and it is depending on, and that depends on the distance. Okay, and all of them, it is finally you compute, you compute this force, that is attractive forces less the repulsive forces. Okay, that is how it works. Okay, here we use, for the anticipative dynamic planning, we use one planner that is called RRT. I don't know, probably some of you know that, but it is, I am not going to explain in detail that, but it is a sampling-based planner, then using only samples allows to create what is the trajectory to reach, to do the plan for going from one position to another. And it is this anticipative dynamic planning use the people intention, that is the prediction of the future, what is going to be the people, and use the RRT, that is this planner, that is this part here, and using both, try to avoid the person, the people, where the people is going to be, and try to reach the goal where they have to go. Okay, the robot has to go. And usually it uses, although the object could be far away, it uses an observation close to it. Usually, in this case of the robot that is moving around 0.8 meters per second to 1.2 meters per second, use 5 meters of horizon, and then although the object, the point to arrive is far away, that could be the point that is closer to that, and then it tries to go here, but at the same time it computes path to different position of this horizon. Okay, and then here you can see shortly we show that the robotic platform, that is this planet simulation environment, and then you can see this horizon where it has to be where the robot was to go, and there are the different plans. There is the computation of different plans, and from all of these has to look for the best plan, and the best plan will be this one. Okay, and that is what the one that will be computed. And here is the motion of the people and the motion prediction where the people is going to be, and is going to interact or not with the robot path, and then it has to change every time in order to find the right one. Okay, okay. Okay, I'm gonna go further because I have not more time. I will not explain that. There is the different cases of a company, robots and persons, and there are, in this case, a company one person, and you can see this one here with these vortices that implies the prediction of the people. Also, we have done that with flying robots. In this case, it's a human and a robot then the robot is the UAV, and the person is, in this case, is this here, and you can see here the real experiment. Here you see the person that is moving, in the robot that is the drone, and then it has to accompany, this drone has to accompany the person, and follows very similar I have shown before, but in 3D. Instead of being 2D, it's 3D. Okay, this I go.
Alberto, you have 4 more questions at the chat, please.
Okay, let me see. Edison said, what platform do you use for robot simulation? Well, we use we use ROS, okay, and we use the platform, depends. Sometimes this robot TV use Seedway, and it has Seedway is a differential platform configuration. In other case, we use steering configuration. In another case, we use Ackermann. That depends of the robot that we are using. Pablo says, may you upload all the slides on Drive and share? I will slide. Yes, I can give you this. And Carla says, what methods or tools are used to predict trajectory? We use different kind of predictors. We use Bayesian predictor, for example, that is a very basic one. We use convolutional neural net predictors. We use different kinds. I will show one of these later on in this presentation.
And Angel Lopez has another question before about ROS1 and ROS2.
No, ROS1, I say we use now ROS1. We're moving to ROS2, but at present everything that we have is ROS1. Okay, and the examples that you will use for the workshop is ROS1. Okay. Okay, there is. I'm not going to explain that. That is the information. Take a look at this. What happened in this case? We are accompanying one person, but take a look what happened here. The robot has to detect that and react to that, and the robot has to react accordingly. It has not a stop, but has a slow down. It has modified slightly the motion in order to continue. In this case, is accompanied to persons. Okay. Okay. Now let's going to see that for Hanover operation. It's a Hanover task. It's another task. And taking account what happened here, there is a robot and a person is moving, and finally the position is this, where the giver, that is the person, is going to give the object. Well, in this case, it's the robot, but it could be the reverse. It's going to be the object, and the robot has to pick up this object, and then finally the person release the arm, and the robot release the arm and go away. But this is first phase is approaching, second is pre-contact, third is contact, and third is release. That is a typical action. And in here, the robot has to understand the intention of the person, the motion in the approaching, and also the intention of the arm, the motion of the arm. And then the robot has to anticipate or adapt to that in order to pick up the object. Okay. Now, this is very similar to the before. You can do implicit or explicit intention, and also compute, do the situational awareness, do the collaborative roles and plans, and finally, in this case, they take the collaborative action. You can see here, we use in this case convolutional neural net, and it's an anticipation deep learning. We use different channels of, one is to take the information from the skeleton, another is part of the skeleton, another is information from the arm of the robot, and all this information is doing with a neural net. We learn all this part here. There is learn this part, we learn this part, we learn this part, and then we fuse this information, and then we have a predictor of the 3D skeleton and motion. But also, we predict the intention of the person. We don't not only predict what is going to be the arm and the human body, but also we predict the intention of the person. Okay. Now you can see here on a video what you will see what there is another of the models that we have different models of attention models. And you can see In this case, is the robot that is giving the object and the person is picking up. And in here, the prediction of what is going to happen is the prediction of the motion. You can see here the future pose is the green and yellow, and that is the real motion. Okay, and then there is what is real motion and what is the prediction. And then we have an uncertainty of the prediction that is, you can see in this cube, that is the uncertainty of it. Well, it could be this here, or is inside of this. Usually it's a ball, but in this case we give. Okay, let's going to see something similar in object transportation. And in this case, both the robot and the human has a slide bar, and then they have to be together. In this case, there is this object is very light, and has not really weight, and is not touching neither the ground. However, is a way to understand what are the relation between the human and the robot through the sensor. There is a sensor force that is here, and also the position of the person. And then in here, the robot has to anticipate the motion plan, taking into account the company person, and also has to anticipate the motion plan, taking into account also the obstacles that are in between here. Okay, and then similar to that, we have to take the implicit and explicit intention, and also compute all these part of the forces, and also compute the collaboration action. Okay, you can see here one example of the human and the robot that is part of our experiments we're doing together. And in some of these cases, the robot acts as a master and the person is the slave, or vice versa. The person is the slave, is the master, and the robot is the slave. Or could be that they both work in a cooperative way. And in this case, for example, the robot detects then is a narrow path, and then they give the possibility that the person change the position of the arm in order that they both then can pass this without colliding. Okay, there is another example. Let's going to see another one where human and robot do searching of an object in a large space. There is a human and the robot that do this task, and the robot has to know the intention of the person and know where the person is exploring, and also can give to the person what is the best trajectory to do. They are sharing this information through the same, that we have the intention, we compute the situational awareness, and we do the plans, okay? But in this case, both we have robot person, and they're looking in this area, it's a very large area, they're looking at one object specifically that is located in one place. They don't know what it is, and they have to explore the area in order, in a way that the person explore, the robot explore, and both, if they find the object, they give to each other, but if not, they know where they have explored, then they have not repeat to explore that area. In this case, they use a mobile phone where they share the information. So the robot sends the information through this mobile phone, and gives information where the robot is, where is the plan to go, and what is the plan that the robot is going to do. And the person can give the information where he intends or she intends to go. And then the robot knows where the person wants to go. Then it plans the trajectory to go. It plans its own trajectory, and then the area that has been explored is known by the robot. It's also known by the person through this information, and then they it's a way not to repeat the area to be explored, and then they can sharing this information that is you can see here.
Sorry, Alberto, we have 3 minutes.
We have what?
And one more question. 3
Okay.
minutes to the end of the session.
Yeah. Mario says, in these settings, what is the difference between implicit and explicit intention? Implicit is the implicit intention is something that the robot can know through the perception. Looking the previous path can know what is going to be the future. Explicit is when the intention of the person has to be given because it tells something to the robot, or because it's pushing a button to say, I'm going to do that, or something like that. That is what the difference between implicit and explicit. Okay, in this case, there are, I cannot give in detail, but there are different, we use a planner that use that maximize some team objective using agent rewards, environment rewards, task rewards, and interaction rewards. And you can see here which are the rewards, but I cannot give in detail what is that, but that is a way to compute what is going to be the best reward, and in this case can compute both what is the best plan to do each other, okay? And there is a video here that I can only show very short of that because we have no time for that. And there is what is the motion of that. The person give through this mobile phone the intention and what they want to do, and they can say what is going to be the plan that is going to do. The robot is going to say exactly the same, and every time both are sharing this information and the area that has been explored up to arrive to a point that could be that one detects what is the object and then finish the task. And you can see here the explored area, what it is of both of the person and the robot itself. Okay. Now, finally, I'm going to show you the harvesting and pruning. That is something that we are doing now. We try to cut, to detect what are the grapes to be picked up, and then detect the peduncle, and then give instructions in order to cut that. That can be doing by, that is for harvesting, and it is for pruning the arms, the tree branches, I'm sorry. And there is something similar, what we do here. And you can see here, this is the detection of the grapes and detection of the peduncles. And in here, you can see the human prediction. That is the human doing, a farmer doing tasks typically of for harvesting. And then we predict, you can say, well, in this case, we detect the skeleton and we predict the next action and what has to be done by the robot, okay? And there is this collaboration between both is when, for example, the grapes are occluded by leaves, and then the person has to take away the leaves in order that the robot can pick up. For example, that could be one. Or could be when the object has to the grapes has to be given to put in the box, or to signal what is the point to cut the branch, or to pick up what is the grape that has to pick up. This kind of collaboration is what we are looking for. Now, next, in 2 weeks, we will be in Rome, where we have to do this kind of real-life experiments with this kind of grapes, okay? And thank you. That's all for my side. And I will put this.
More questions here by Carla and Angelo.
Okay. Carla say, what is the mathematics is used to create these formulas? Well, here we use basically typical mathematics that you know. This algebra, basically we have matrices, basically what we use. We use nothing special difficult for you. I mean, probably, okay, we use sometimes a live algebra, or we use a specific kind of algebra. Yes, we use Fourier descriptor, something like that. But that is something that probably you have studied in your grade or in your bachelor, I mean, or I think most of the mathematics that we use are not specifically complicated. And what it says here, Angelo says, for robot motion planning, they use topological and control theory. Say we use, well, topology we use always, because we use geometric, we use topology, We use graphs, we use trees. By the other side, we use control theory when we have to, when it's basically the control of the robot itself in the very low level. We use all the part of the control theory. But in this case, for example, the controllers that we have used here are typically very low level controllers. Proportional integrated differential controllers. That's typically what we use. In some cases, we use model predicted control. Yes, so that's the difference.
Okay.
And that's all. I don't know if you have any other questions, but if you want, later on, you can communicate with me and I can give additional information.